Previously, we talked about tests where samples were independent from each other, mostly. Here, we're going to look at tests involving paired differences. These are dependent samples. And so, an example of a dependent sample might be if you were a teacher and you're comparing your class's pre-test scores and post-test scores, and seeing if the difference in pre and post-test scores was a significant difference or not. So our focus points here are to be able to identify paired data and dependent samples, explain the advantages of paired data tests, compute differences in the sample test statistic, which will either be a z or a t-score, to estimate a p-value, and to make test conclusions. First, paired data. Many statistical applications use paired data samples to draw conclusions about the difference between two population means. Data pairs occur naturally in before and after situations where the same object or item is measured both before and after a treatment. Applied problems in social science and natural science and business administration frequently involve the study of matched pairs. A business might look at store sales before and after a new advertising promotion, or before or after personnel changes. Psychological studies of identical twins, biological studies of plant growth on plots of land that are matched for a similar or different, I should say, soil types, moisture, sun exposure, business studies are all examples of paired data studies. When working with paired data, it's super important to have a definite and uniform method of creating data pairs that clearly utilize a natural matching of characteristics. We'll take a look at this now. A shoe manufacturer claims that among the general population of adults in the US, the average length of the left foot is longer than that of the right foot. To compare the average length of the left foot with that of the right, we can take a random sample of 15 US adults and measure the length of the left foot and then the length of the right foot for each person in the sample. Is there a natural way of pairing the measurements? How many pairs will we have? Well, yeah, there's a natural way. It's each person's left foot with their right foot. And we're going to have 15 pairs since we are going to have 15 people in our survey. When we wish to compare the means of two samples, the first item to be determined is whether or not there's a natural pairing between the data. So this could be from before and after situations, from matching data by using studies of the same object, or by some process of taking measurements of closely matched items like a person's left foot and right foot. When testing paired data, we take the difference D of the data pairs first, and then we look at the mean difference D bar. Then we use a test on D bar. Theorem 8.1 just shows how this works. You don't need to know Theorem 8.1, but it simply tells us how we would find t-scores from this. If we have a random sample of n data pairs, like n pairs of feet, suppose the difference d between the first and second members of each data pair are approximately normally distributed, with a population mean of mu sub d. Then the t-value is computed like that, where d bar is the sample mean of the d values, n is the number of data pairs, and s sub d is the sample standard deviation of the d values. This uses a student's t distribution with degrees of freedom n minus 1. When testing the mean of the differences of paired data values, the null hypothesis is always that there is no difference among the pairs. That is, the mean of the differences, mu sub d, is 0. So this will always, always, always be your null hypothesis in paired dependent testing. The alternate hypothesis depends on the problem. It could be either a left-tailed one where it's less than 0, a right-tailed one where it's greater than 0, or a two-tailed one where it's just not equal to 0. For paired difference tests, we make our decision regarding the null hypothesis according to the evidence of the sample mean d bar of the differences of measurements. We then convert the sample test statistic d bar to a t-value using a formula. We are going to use a calculator to do that instead. To find the p-value, we will also use the calculator. So the general procedure: obtain a simple random sample of n matched data pairs, A and B. Let D be a random variable representing the difference between the values in a matched data pair. Compute the sample mean D bar and the sample standard deviation S sub D. If you can assume that D is normally distributed or is mound-shaped and symmetric, you can use any sample size. If you can't assume this, use a sample size of at least 30. We start, as before, in previous sections by setting the null hypothesis and the alternate hypothesis. The null hypothesis of no difference in this case is always going to be this. It will always be H sub 0 such that mu sub D equals 0. That is always our null hypothesis of no difference when we're testing paired differences. The alternate hypothesis will be one of these three choices. It will either be mu sub D greater than 0, mu sub D is less than 0, or mu sub D is not equal to 0. We also at this stage set our level of significance, alpha. Then we find t-scores. We're going to find those using the calculator. We're going to find the p-value that corresponds. And then we conclude the test just as we've done previously. If the p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value is greater than alpha, then we do not reject the null hypothesis. And then we interpret our conclusion. So a team of heart surgeons at St. Anne's Hospital knows that many patients who undergo corrective heart surgery have a dangerous buildup of anxiety before their operations. The staff psychiatrist has started a new counseling program intended to reduce this anxiety. An anxiety test is given to patients who know they have to undergo surgery. Then each patient participates in counseling sessions with the staff psychiatrist. At the end of the counseling sessions, each patient is retested to determine anxiety level. Table 8-8 indicates these results. So for example, before counseling, Jan's anxiety score on this measurement was 121. Afterwards, her score was 76. That's a difference of 45. Tom's score was 93 before. After, it was still 93. No difference. Barbara's score, I'm skipping down just a little bit. Barbara's score before was 115. After counseling, it was 117. That difference then is -2 because it's B minus A. So if the difference is positive here, the anxiety decreased. If the difference is negative here, the anxiety increased. And if the difference is 0, there was no change in anxiety. Higher scores mean higher levels. We're going to assume the distribution of differences is mound-shaped and symmetric. Can we conclude from this that the counseling sessions reduce anxiety? We're going to use a 0.01 level of significance. Before we even begin, we have two important points. We have a random sample, so that's good. And we have a pair of measurements taken on the same patient. That's good. That means we can do a paired difference test. The sample size is only 9, but that's okay because we are saying that we are assuming the distribution is mound-shaped and symmetric. Since we're assuming that, we can still proceed. Otherwise, we need at least 30 samples. So we've already noted our alpha needs to be 0.01 and our hypotheses. So our null hypothesis is going to be that the difference in the mean mu of anxiety is 0. Now, our alternate hypothesis is that this is reducing anxiety, and so that's going to be a positive difference. Remember, in our examples here, so like Jan's score, anxiety score, went down by 45, but that's positive, right? So we're seeing that if it actually does decrease, the mean of differences should be positive. This is important to read the problem carefully because we might think, oh, well, we want it to go down, so that's going to be negative. No, 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 no. Read the problem carefully. Can we use student's t here? Yes, we can, because we can find a standard deviation s, and we can use t also because the data is approximately normal. To do this on a calculator, we go to Stat and we go to Edit. We're going to put this information in some lists. And so what we're going to do is we're going to put our score before counseling in list 1. Our before scores are always going to go in list 1. Our after scores are always going to go in list 2. So I'm going to pause and do that right now. So as you can see, I've input my scores into list 1, my score before counseling, and list 2, my score after counseling. It's going to be important that you double check on your work. The first time I did this, I had typos and it messed things up. So you don't want those. So I always do at least a quick double check. How do we find this? Because this is what we really need here. We need D for difference. So to find that, the calculator will do the work for us. And in this, it's a little bit like almost like Excel would do. We go to list 3. We use the cursor key to go up to that very top, to that header row where it says L3. Then we push the second key and the number 1, and we see that L1 shows up. Subtraction key, second key, number 2 to get L2. Then hit enter. And what it does then is it subtracts list 2 from list 1. And again, we want to check these values against this column here to make sure that we don't have any typos. And here we don't. So again, to do that, you go up to where it says L3. In that very top row, second key, number 1, that's list 1, minus second key, number 2, that's list 2, and hit enter. And that will do that. If you make a change in one of these lists, if you realize later you had a typo and you go back and change it, you have to do this step again. It doesn't automatically update. So it's not like Excel. If you've used Excel, you know that if you change a value, Excel will update all the formulas that use that value. That doesn't work on the TI-84 on the lists to do that. You have to do it. You have to go and do that again to get it to update. Once that's in there, then I go to Stat and I go to Tests. I'm going to choose a t-test because I don't know what sigma is. I hit enter. Instead of using stats, I'm using data. Because I'm looking at a paired difference, my population mean here is, or really is the mean of my differences, is 0. For my list, I choose list L3. So if that's not chosen, and it probably won't be the first time you do this, hit the second key and choose number 3. So second and a number will always give you a list of that number for up through list 6. Don't worry about frequency. Here, we can do whatever type of test we want. Here we're saying our alternate hypothesis is that we think the data is actually greater than the null. So we're going to choose the greater than test. We then hit calculate. We get a t-score of about 4.362, and we get a p-value of 0.0012, which is less than 1%. So let me write those in here. We have our t-score of approximately, I should make the approximate sign there, but I'm not going to, of approximately 4.362. And we have a p-value of approximately 0.0012. From this p-value, then, we can make some conclusions about our test. Specifically, our p-value of 0.0012 is less than or equal to our alpha value, which we set at 0.01. So because 0.0012 is less than or equal to 0.01, we reject the null hypothesis. We reject the null hypothesis. We have evidence that the data indicates that counseling sessions do decrease anxiety in this particular population of patients. So at the 1% level of significance, always put the level of significance as part of your interpretation. At the 1% level of significance, we conclude that the counseling sessions reduce the average anxiety level of patients about to undergo corrective heart surgery. Notice, we aren't making a claim about how much it reduces it. Okay. All we're saying is that the counseling sessions reduce average anxiety of this particular group of patients. And so we couldn't claim from here then that counseling sessions would also reduce anxiety level of patients about to undergo chemotherapy or about to undergo brain surgery or about to undergo anything else. It's one particular group. Now, we might use this as a starting point for further research, but all we can conclude from this test and this data is for this group of patients. So I hope that is beneficial for you. The trickiest part of these is just, I think, getting into your calculator and knowing what to do. Again, you're going to go into our stat menu, and the first thing you'll do is you'll edit and you'll put in the before scores are always in list 1, the after scores are always going to be in list 2, and then list 3 is before minus after. Then we'll use list 3 as our data for when we go to our t-test. Remember, we use the t-test here because we don't know sigma. So remember, when we're looking at paired differences, our population mu or our null hypothesis mu is always going to be 0. And make sure you use the right list here. If you put list 1 or list 2 in here, you would get the wrong answer. So make sure you're using the list that has your differences in them if you're doing a paired difference test. If you have questions, please let me know. Good luck moving forward.